Hello everyone, and welcome to this new appointment with the Toro Vergata Astrophysics seminars. Today is a great pleasure for me to introduce Alessandro Sozzetti. Alessandro got his degree in physics at the University of Torino in 1997. Then, after a visiting experience at the Space Telescope Science Institute, he moves to the University of Pittsburgh, where he got the PhD in 2005. After the PhD, he had some research experience at the Osservatorio Astrofisico di Torino and at the Harvard-Smithsonian Center for Astrophysics. And Alessandro is currently a field researcher of the National Institute of Astrophysics at the Osservatorio Astrofisico di Torino. His main area of expertise are stellar spectroscopy, astrometry, high-precision radial velocity, and photometry. He works on the detection and the physical characterization of extrasolar planets, as well as on the characterization of the star which hosts those exoplanets. In this respect, he is involved in many projects and space missions like Plato, Ariel, TESS, Cheops, and ESPRESSO. Today, Alessandro will talk about the demographics of exoplanetary system, the state of art, and future prospect. So, Alessandro, if you are ready, I leave the floor to you, so you can start.
Many thanks for the kind introduction. It's a pleasure to be here, if not in person, at least some way to be able to share with you some, let's say, interesting snippets of a particular area of exoplanetary science that is a focus of many projects in which Italian researchers are involved. I will provide an overview of the state of the art of planetary system demographics and try to place here and there small elements of key contributions provided by the Italian community through, in particular, observational channels with high resolution spectroscopy. And then I will give a general overview of something that is to come in the next decade or so in terms of fundamental contributions to the field through important programs, both from the ground and in space, again, in which Italy is involved in key aspects. So let's get immediately into the nitty-gritty of some of the aspects of exoplanet demographics. The way to look at the population of planetary systems known today through a mass versus orbital period diagram allows you to understand the variety of exoplanets that have been uncovered by a handful of different detection techniques, all with their different biases. Some are most sensitive to very close-in planets, typically rather massive. Some are particularly sensitive to very low mass companions, still at very short orbital separations. Some others are particularly sensitive to wider separation companions. Overall, in a diagram such as this, one can immediately understand how the population of known exoplanets essentially spans most of the region of the available space as it is being probed so far by techniques. The two most successful ones are the radial-velocity and transit techniques that allow you to infer the presence of a planet through dynamical effects. This is the Doppler method, or through geometrical alignments that are particularly favorable. This is the planetary transit technique through photometry. These two techniques has really contributed the vast majority of the companions that are known in this diagram at, let's say, short and intermediate separations, up to maybe a couple of astronomical units. And the regime of wider separations is typically in the hands of two other relatively important contributors in terms of detections, which are the microlensing and direct imaging techniques. As you see from this diagram, clearly something like an analog of the Earth with the orbital period and the mass of our planet is still to be uncovered. And this is one of the key aspects in which more progress has to be done in terms of exoplanetary system demographics. What is the field of demographics? Well, it essentially encompasses the identification of the distributions of all the relevant orbital and physical parameters of planetary systems, and the identification of any trends and correlations in these distributions, and their and the way they unfold into allowing people to estimate occurrence rates of planetary systems of different types. The way this is typically done is to compute the number of planets as a function of a specific parameter, one or more. And in this way, any distribution function that you can determine in either mass, radius, composition, separation, and the likes, essentially tells you something potentially very deep in terms of fossil evidence of the fundamental processes at the heart of planet formation and evolution. Once you have these distributions, the next step is to compute occurrence rates. This is in principle very simple operation to do. You have to compute the number of planets divided by the number of stars to which the planets you have detected were sensitive using your technique of choice. This is not at all a trivial task, and this turning distributions into occurrence rates is something that you have to do very carefully, taking into account, in particular, these two aspects, the completeness and reliability of your survey program, regardless of the technique of choice. This is not at all a trivial task. I will try to give a broad overview of many of the aspects in terms of distributions, trends, and correlations that I provided here. It is not possible to cover everything in just 45 minutes, so something I have to keep out, and in particular, I will not touch upon the effects of stellar binarity in the statistical properties of exoplanets. One fundamental point to bring home is concerns the distributions of the two fundamental physical properties, the most fundamental physical properties that we like to measure for planets. These are the mass and the radius of a planetary companion to a given star. And as you see here, we already know since almost a decade that the planetary mass and planetary radius distribution functions are clearly rising towards lower masses and lower planetary sizes. Such that typically, whether you use radius or mass as a proxy, very low mass or very small radius objects can be as many as 10 times more frequent around stars, for example, similar to the Sun in spectral type, than giant planetary companions. The way people have addressed this issue has improved with time, and higher, let's say, the final structure of some distributions, such as the radius distribution, has become possible to investigate thanks to improved quality in the treatment of the data, and in particular, thanks to the fundamental contribution from space-based transit photometry, in particular the Kepler space mission. The radius valley that you saw very tentatively in the previous slide is actually a very well-established feature today. What we notice is not a monotonic increase of planetary frequency towards increasingly smaller radii, but there is a bimodality in the distribution that identifies two clear peaks in the interval of approximately 1.5 and 2.5 Earth radii. These two peaks are separated by a valley, and this gap in planet size is called, as a matter of fact, radius valley. This is really a very prominent feature in the radius distributions of small planets, and it separates effectively two populations of planetary systems that are identified today as being so-called super-Earths, primarily rocky in composition, and sub-Neptunes, objects with still smaller radius than that of Neptune, so between 2 and 4 Earth radii, that are definitely of different composition. They are not rocky. They may be having sufficient contributions in decompositions from volatile elements or even gaseous envelopes. There is a very fundamental aspect to be indicated in this presence of a valley in the radius distribution that is related to the evolution of these companions. These objects are all very close in. They are mostly residing at of order of a tenth of an astronomical unit as a typical ballpark number. So they're very highly irradiated. And in the diagram in the right, you see that very high radiation levels correspond potentially to different structures in different compositions for objects of smaller or larger radii, as a signature of having undergone or not having undergone significant photoevaporation. This is essentially the key element of knowledge that one can bring home in terms of understanding why we have today the presence of a bimodal distribution in the small size radii of planetary systems. If you have available both mass and radius, then you can enter in a mass radius diagram and study even more in detail the actual structure and composition of these companions. The mass radius diagram is a tool that has been used to study the population of planetary systems since now almost 20 years. And today, the populations of these larger and smaller planets allow for in-depth understanding of their structure. And in particular, when you come to the comparison with solar system planets, you see essentially the extreme diversity or potential differences in composition of the known exoplanets that essentially cover almost without discontinuities the full range that is encompassed here. Planetary mass and planetary radius allow you to do a variety of exercises. The simplest one that has been done routinely is to compute a mass-radius relation in terms of a simple power law fit. This has evolved in time. As you see here, various representations of the way people have, in fact, fitted mass radius versus radius relations. The fundamental element to bring home today from a diagram such as this is that almost certainly a simple power law straight across a vast radius of masses and radii is probably not enough of an explanation for the observed spread in masses and radii. If you focus on the small size companions, let's say smaller in radius than the Neptune, and with a mass up to 30 or so Earth masses, you understand better what I mean. Here, the spread in potential values of radii, for example, at a very almost perfectly fixed value of mass, let's say 10 Earth masses, is very, very significant. This is not the case very much if you get to smaller masses, where the spread in possible values of the radius gets increasingly smaller. This is one fundamental diagram that I like to show as one of the key aspects to which the Italian community has contributed through access to the high-resolution spectrograph HARPS-N, the Telescopio Nazionale Galileo, of the population of objects that we see here represented with very good mass measurements, better than 30% in precision in mass, comes from HARPS-N observations. And this is really a very significant contribution to the understanding of the structure of these very small size objects. Just to give a very specific example, I show you the statistics. This is an example, a very recent example of the contribution of HARPS-N in understanding what could be the driving formation mechanism for objects of specific types. This is a case of a planetary companion uncovered by the TESS mission. And with the accurate mass measurement from HARPS-N, the planet is TOI 1235b. It orbits a low mass star, an M dwarf, and it is located in the middle between these two regions, these two curves that identify the slope of the radius valley that you have seen already in the previous diagram. That is determined by theories that explain the presence of the valley in terms of mass loss due to a photoevaporation, or mass loss simply because the planet has formed in gas-poor conditions in the late stages of planet formation. The two curves create a shaded area in which planets, if they fall there, they are supposedly of very different composition depending on whether they happen to arrive there through photoevaporation or because they formed in gas-poor conditions. In this case, TOI 1235b is understood as being rocky, and rocky composition is something that is entirely predicted by mass loss through photoevaporation processes, and instead not by the gas-poor formation scenario. So in a case such as these, keystone objects, such as the ones that are being measured through the contribution of the HARPS-N instrument, allow you to actually test directly theories for this specific aspect of the planetary population. Going back to general features of distribution functions, this is a very intriguing aspect of the mass function. We have seen it rising towards lower masses in an essentially inequivocal manner. If instead of the mass function, you use the mass ratio as the key parameter, you actually notice a break at some point. The probability of the likelihood of a planet being hosted by a given star does not increase monotonically with decreasing mass beyond a certain point. This is something that is measured regardless of the measurement technique. On the right, you see the feature identified through microlensing measurements. On the left, instead, you see the same mass ratio parameter using Doppler measurements. And this is a very interesting feature in the mass function, in the mass distribution, that tells you probably something very fundamental in terms of planet formation and evolution. In particular, what would be the most informative parameter to use, whether it is mass or mass ratio. There are interesting surprises, even and potential, let's say, things that make us head scratched. If you look, for example, instead at the distribution of orbital periods, occurrence rate grows with orbital period for giant planetary companions up to a point, according to some studies. And the region in the left up diagram with the different colors identifies approximate locations of the so-called snow line beyond which we are expected to have most of the planet formation for giant planets going on. Approximately at the snow line, there seems to be, according to some studies, a break in planetary frequency that begins to decline rather than continuously rising at wider separations. This is not the case if other investigations with the same measurement technique, here in this case, in both cases, we are looking at the Doppler surveys, and the comparison between these potentially not at all in agreement results tells you something probably fundamental about the way different survey programs are being analyzed. Another key parameter that is extremely informative in terms of understanding planet formation evolution is the eccentricity of orbits. In an eccentricity semi-major axis diagram here, you see the population of known exoplanets essentially covering the full range of potential eccentricities that an orbit can get. Planets can be extremely eccentric, can also be rather circular, and whether an orbit at a given orbital separation is very eccentric or very circular tells you something about the fundamental processes that actually made it appear as it is. In general, high eccentricity systems, regardless of their orbital separation, are an indication of possible violent history of the initial stages of formation and orbital evolution. While very round orbits imply almost certainly, or at least to a good extent, especially in a certain regime of orbital separation, not at all violent formation history and evolution history. A very key contribution to this study of eccentricities has come again thanks to a fundamental contribution from the HARPS-N spectrograph. In this case, you see a different representation of what we have seen before. You see the so-called Untitled diagram that expresses the mass ratio between the planetary mass and the stellar mass as a function of the scaled semi-major axis in units of the stellar radius, of the planetary radius, sorry. In this diagram, objects with very high eccentricity are the blue squares. Planets with essentially no detectable eccentricity that are compatible with essentially being fully round orbits are the open squares and the crosses. The fundamental line to take into account is the lightly dotted line that separates essentially almost entirely the population of eccentric and circularized systems. Not completely, but almost entirely. And that is the line that corresponds to a circularization timescale of a closing giant planet on a typical orbital period of just a few days or so, at approximately 1 giga-year of age. So from this diagram, one brings home the fundamental message that objects that have not had yet the time to get circularized are oftentimes definitely eccentric. And that means that this population of objects on a relatively, let's say, somewhat wider separations, they are most of the time eccentric. That means that very effectively, high eccentricity migration has been in place at the early stages of planetary systems life. The planet-star connection is another key aspect that has been investigated since the very beginning of the studies of planetary systems. There are two fundamental connections. One is how planet frequency varies with stellar mass. In the case of giant planets, this is today well understood as being an increasing quantity with stellar mass. And so giant planets are increasingly more frequent around increasingly high mass stars, up to a point. The break in the rise of planetary frequency with stellar mass is possibly around 2 solar masses. Although, again, because of the difficulty in understanding exactly the details of the surveys and oftentimes small number statistics at a very high primary mass, and this is still a matter of debate. The other fundamental quantity that has been cross-correlated with planetary frequencies is stellar metallicity. The chemical composition of a star has an important impact in planet formation, in particular for giant planets. On the left diagram here, you see that planetary frequency for gas giants is a very steep increasing function of increasing stellar metallicity. In the case of lower mass or smaller size companions, and this is a case on in the lower right diagram, separating the population of Neptune size and super-Earth objects from the larger size objects in the Kepler field, you actually notice that probably planetary frequency for small size objects is not very much affected by variable stellar chemical composition. When we move to a regime in which other techniques essentially have the best of their effect in terms of, for example, of direct imaging techniques, we're looking at very wide separations. This is the regime in which direct imaging works and operates primarily around for planet detection around very young stars. Today, the relatively still small number statistics provides one fundamental element of inference that is still compatible with one of the trends that we've seen before through a particular Doppler surveys. And it is the fact that it appears that the very high mass tail of the planetary mass distribution seems to follow the trend of increasing frequency with increasing mass of the stellar primary. There is not much more that can be said with this technique so far, because essentially of the lack of statistics. We are moving towards the end of the summary of the things that can be said in terms of state-of-the-art demographics. I like to spend a few more slides on the contribution of multiple planet systems statistics to the lot. The first thing that we have seen so far is being planetary frequency in terms of frequency of planets of a given type around stars of a given type. This is a reminder of the same concept, particularly for Kepler planetary systems. And here you see an inverse dependence for small size planets with respect to the trend with mass of the central star that we're seeing for Doppler planets. In this case, planetary systems are particularly frequently found around increasingly lower mass primaries. Planetary frequency, so the frequency of stars with planets of given properties, can be turned into a different question: how many planets are orbiting a given star? And this brings us to the point of planetary multiplicity. Even in this case, the number of planets orbiting a given star, if we use, for example, the Kepler planets as a sample of choice, appears to follow the same trend. And so there is higher multiplicity of planets identified around lower mass stars than the opposite. And the difference appears to be rather significant. Almost a factor of 2, if not more, in terms of number of planets hosted by, let's say, F-type dwarfs, real spectrum dwarfs. Multiplanetary systems are extremely diverse. We've seen the general diversity of the sample, and if we look at multiple planet systems, the diversity is even more transparent. As of today, we still have to find a real true analog of our solar system. You see it, for example, in the comparison with the radial-velocity detected and the transiting systems in the left panel. What we know today, particularly thanks to the Kepler mission statistics, is that planetary multiplicity can be pretty high. Say, typically stars in the Kepler field can be almost the same level of frequency, having 1, 2, 3, or even 4 companions, while even higher multiplicity begins to drop. Multiple planet systems have very interesting fundamental parameters that can be measured, and their variations appreciated. In the case of small size companions in the Kepler field, eccentricity and mutual inclination angles are 2 fundamental parameters that can be measured rather well, and they provide key insights on the history of how we call the dynamical temperature evolution of these systems. In particular, the 2 fundamental aspects to understand are the fact that as a function of increasingly higher multiplicity, the typical eccentricity of the systems decreases, as well as the typical inclination with respect to the line of sight of these systems decreases. So higher multiplicity systems are increasingly flatter, with essentially almost the same inclination with respect to the line of sight. So that's why they are all found in transit. And they are also increasingly rounder in terms of orbital configurations. So there is a combination of how we call them dynamically hot and dynamically cold systems, where the dynamically cold are the ones that are essentially quiet in terms of low eccentricity and very small mutual inclination, while the dynamically hot systems are those where eccentricities are significantly different from 0, and mutual misalignment in the orbital configurations is somewhat significant. And to conclude the excursion on planetary systems, this is one very, very intriguing aspect of the statistics in the Kepler field that has been covered in the last couple of years, and is the so-called peas in a pod effect. If you look carefully to a selection of multiple planet systems, like the one in the left, you may notice that multiple systems appear to be similarly spaced and similar in size. There is in fact a very clear correlation between the size of the outer and the inner planet in a given pair of multiple systems, and the let's say similar sizes, similar spacing effect is actually being established on extremely solid grounds. This tells you something about the way these planets are formed. What it's telling us exactly is still a matter, however, of debate. Multiplanar systems have still something to tell you if you look at a combination of techniques that can be put together to show you, for example, the power of combining direct imaging and Doppler measurements to uncover the architecture of systems and over a very wide range of orbital separations. And two very key elements of formation that appeared recently in the literature are connected to, for example, the fact that we often find an additional very wide separation companion in systems in which we already find a giant planet relatively close in orbit. And there is also a very clear connection between the presence of an inner small mass, small radius system of planets with super Earths and Neptunes relatively close in, and an outer giant companion. In both cases, whenever you find something in the interior, in the inner regions of the planetary system, there is often something else outside. To conclude, this is one probably of the most relevant plots that one would like to make once and for all. This has been done many times, and it's the calculation of the occurrence rate of planets like us, Earth-like companions, meaning objects that receive the same radiation level as our Earth, and the orbit a star similar to that of the Sun. This calculation has been performed since the last decade, many times. Today, let's say we are probably converging about an occurrence rate of Earth-like companions on the order between 10 and 20%. This is, however, a number that is essentially an extrapolation, because so far we have yet to detect one such object. The closer we have gotten so far is again thanks to the contribution from the HARPS-N spectrograph and the involvement of the Italian community in the field. And it encompasses the identification of a potentially habitable companion in the habitable zone of its host star in a multiple system seen in transit. The star is K23. It is not a solar type star, but it's the highest mass star around which we have been able to provide at least the first inference, not only of the size, but also of the mass of a companion in the habitable zone. K23d, which I indicate here in the diagram, is probably a very low density object, as only a preliminary mass estimate, because even on the face of several hundred measurements of radial velocities with HARPS-N, it is still not been possible to pin down very accurately its mass, but it's the closest we've gotten so far to identifying the two fundamental physical properties of a habitable zone companion around a star not too dissimilar in mass from the Sun. So I will now switch quickly to the future. There are many open questions in the field. I list here some of the most fundamental ones. I have touched upon most of them in showing you the correlation and trend diagrams in the first half of my presentation. The thing that has to be kept in mind is that many of the things that we are seeing may change in time, not just because of increased statistics, but because of increased understanding of the properties of the survey programs, and in particular, better measurements of the better determinations of the completeness and reliability. This is something that has to really be kept in mind. 2 points that I want to touch for future aspects. Actually, it's 4, but it's really 2 in which I will dwell briefly. The first is the Gaia mission. Gaia is a global astrometry mission. It measures very accurately stellar positions in the sky. It has been said for a long time that it has the potential to detect planetary mass companions. In a planetary mass orbital semi-major axis diagram you see here, let's say the detection curves corresponding to the Gaia sensitivity. I want you to focus on the violet ones, both the dashed as well as the solid line. They correspond, the dashed line corresponds to the Gaia sensitivity, let's say in the solar neighborhood, at around 20 parsecs or so. From the sun, and instead the Gaia sensitivity, the upper curve, corresponds to the location, let's say, of one of the nearest star formation regions, a couple of 100 parsecs away, a factor of 10 in distance or so. The solid curves are the same when you account for a hypothetical extension of the mission that is nominally set to 5 years, doubling its time lifespan, right? Reaching a 10-year mission duration. As you see, the typical regime of planetary masses and orbital separations that for which Gaia astrometry is sensitive is typically few astronomical units, maybe several astronomical units, and we're talking big things. Best case, Neptunes around the nearest stars, but most of the time giants, gas giants, very massive gas giants. Is this interesting today, where we have seen most of the focus of the slides that I have discussed in the small mass regime? The answer is obviously yes, because the Gaia sensitivity to planetary mass companions potentially encompasses millions of stars. And therefore, if you make an educated guess for possible planetary frequencies of such objects as we know them, for example, from Doppler surveys and other techniques, then you come up with numbers that are really spectacular. We are talking potentially about tens of thousands of new giant planet detections, solely based on Gaia data. And based on a nominal mission lifetime. If you double the mission lifetime, Gaia may detect maybe 3 times as many as the ones that I've indicated here. And so the fundamental contribution that we are expecting for planetary system demographics from Gaia is indeed the refinement of the structure of the distributions of the fundamental parameters, orbital parameters and masses and frequencies of such companions to a degree that has never been possible before. It is about to start. And it has not yet started very effectively. The first fundamental contribution from Gaia astrometry will come at the level of data release 3. That is going to be delivered in about a year's time from now, before the middle of 2022. And in the Gaia DR3 catalog, we will find, in particular, here underlined and bold-faced, information on non-single stars that will come through different observational channels. Gaia observes in photometry, spectroscopy, and astrometry. So there will be eclipse binaries, spectroscopic binaries detected, and also astrometric binaries. And the low mass values of the companions identified with astrometry will indeed possibly touch the planetary mass regime already at the level of the third Gaia data release that encompasses a little bit less than 3 years worth of data. So we are definitely not at all using yet all the available information from the Gaia data set. What will Gaia give us can be seen in a variety of possible ways. One way, for example, is to, as I mentioned, is to see how much better we will be able to study, for example, frequencies of giant planets as a function of stellar mass and metallicity. Today, you typically put in a bin of order of 10 to the 2 stars, and Gaia promises to be able to populate these with maybe a couple of orders of magnitude more stars in a given bin. This is what I'm talking about in terms of fine structure of the distributions. Gaia will be particularly important in screening for massive giant planets in the near star formation regions. We may access an order of 1,000 young stars for planet detection. These will typically be very massive companions. And this way we will be able to probe actually this transition region around 10 Jupiter masses that divides planets from brown dwarfs. And especially in the regime of separations that is today mostly not accessible from direct imaging programs. Very briefly, a couple of snippets of the fundamental synergies that Gaia will have, not just by using the data of the spacecraft alone, but seen in combination with other techniques and other detection and characterization programs in planetary science. One fundamental element of synergy is the one with radial-velocity detected companions. If you put in this diagram of the expected astrometric signature as a function of orbital period of the planet, a threshold at approximately 30 microseconds, which is probably the best Gaia will be able to ever do in terms of detection of orbit size, then you see that possibly maybe 50% of the known Doppler detected companions could have a true mass measurement from Gaia. I remind you that the Doppler technique actually is intrinsically a one-dimensional measurement and allows you only to put a lower limit to the true mass of the companion. Conversely, the synergy will also be the other way around. New detections by Gaia of giant planets may ignite follow-up measurements with other velocities to improve the architecture of the system and find additional companions that Gaia cannot. The synergy with Gaia and the direct imaging is not just related to what I said before. It encompasses the interval of possible new generation instruments that will sample a regime of separations to which Gaia is actually sensitive. And so the next generation high contrast imaging devices, for example, on the ELTs, will probe planets that Gaia may have already measured in terms of dynamical masses. And this will clearly, crucially improve the characterization of the direct image companions. And then there's even the possibility that Gaia may find indications of transiting planets that are cold, say orbital separations of an astronomical unit or two. Gaia can in fact measure with a sufficiently high accuracy, let's say, or with an accuracy of a few degrees, quasi John orbit configuration compatible with 90-degree orbit. So it may tell you that there is a potentially transiting planet with an uncertainty of a few degrees. And this will clearly potentially be an element of fundamental synergy with transit photometry programs that may actually look if the planet does indeed transit. There will be hundreds of potentially expected systems with such configurations that Gaia can provide. Most of these will not indeed transit because they are, the transit probability is very, very low, but some might. And so this is the fundamental aspect of synergy with other follow-up and characterization measurements that may provide, albeit small, a sample of companions in transit that are today not at all available. In the future, we will also have two aspects that I touch upon very briefly. The Plato mission will do fantastic statistics, as it has never done before, for the very low mass habitable potential companions. The TESS, KEOPS, and K2 missions that I have just concluded or ongoing now are probing typically the inner regions of a planetary system, looking for transiting planets, small as they may be. Plato really will be able to screen objects if they transit out to 1 AU. from solar-type stars. And so in terms of fundamental contribution to demographics, the Plato mission will indeed tackle exclusively the possibility of estimating in Earth the occurrence rate of Earth-like planets as it has never been done before. In different regimes of orbital separation and masses, other survey programs in space in particular will also contribute greatly. There are expectations with the microlensing technique and the Roman Space Telescope to identify very, very low mass cold companions, several astronomical units of separations that are not detectable yet from the ground. And the next generation of very large space-based telescopes, such as HARPS or LUVOIR, will indeed finally populate with some statistically significant sample the regime of orbital separations at which it is possible to directly detect terrestrial type companions with high in the habitable zone. So the last few minutes on what is to come from the ground. The ground is going to tackle several aspects of planetary system demographics, in particular through extreme precision radial-velocity measurements carried out with a number of instruments that are coming up online now or are being planned for the coming years. The most important of the ones that I list here, because it is now ongoing and it has already provided spectacular results, is ESPRESSO. And ESPRESSO is also a facility in which we are, as an Italian community, significantly involved. That's why I want to show you a couple of very quick highlights of some things that ESPRESSO has provided so far. For one, it is the remeasurement, very high accuracy remeasurement of the minimum mass of the known habitable zone companion around the nearest stars to the Sun, Proxima Centauri. Proxima b has an amplitude of just over a meter per second in radial velocity. It has been measured very accurately with ESPRESSO. The post-fit residuals to the planetary orbit have an RMS of only 27 centimeters per second. You have seen in the previous slide what is the orbit size in terms of the Doppler amplitude of the variation induced by an Earth-like object around the Sun. That's of order 10 centimeters per second. We are not very far from it. This is let's say, a potential breakthrough in what is to come in terms of quality of the data that can come from ESPRESSO, and detection of companions such as the ones that we are really after may be possible with this instrument. Another spectacular element of synergy that I want to, in a second, briefly tell you about, and then I will conclude here, is instead how to use ESPRESSO data in combination with Gaia astrometry, and in particular, an aspect of the astrometry that can be done today before the release of Gaia Data Release 3, combining different catalogs of proper motions separated by baselines of tens of years. This is the case, for example, of the Gaia and Hipparcos proper motion catalog. Two different values of orbital of proper motion in a catalog, the Hipparcos epoch and the Gaia epoch, if they are different, tells you something about the possible presence of an orbiting companion that makes the star wobble in a different direction with respect to the standard direction of the expected linear motion in the sky of the star if it was single. And so the so-called proper motion difference or proper motion anomaly technique can be used to infer the presence of a companion because it can be expressed as a function of the orbital elements of the orbit of the companion. one spectacular experiment we have conducted very recently has been the one that I'll show you here. We have combined the data from ESPRESSO that have allowed to measure very accurately the mass of a transiting super-Earth in a system very next to the Sun, order of 10 parsecs away. This is the Pi Mensa system. This is a very bright star, naked eye star, in fact. The super-Earth has a very short orbital period. It has been detected in transit by TESS, and ESPRESSO has delivered a very high-quality mass measurement. With Gaia and the Parcos, it has been possible to combine the radial-velocity information coming from the data to constrain the orbit of the other known companion in the system. There is a known outer giant planet on a multi-year orbit, on a very eccentric orbit. The combination of the Gaia Parcos proper motion different data and the ESPRESSO measurements have allowed to pinpoint, in fact, the true inclination and full orbital architecture of the outer companion, thereby measuring also its true mass. The knowledge of the inclination and the full set of orbital parameters for the outer companion, and the fact that we know that the inner companion is transiting, has allowed us to measure for the first time, with very high accuracy, a clear degree of misalignment in the order of tens of degrees between the orbits of the inner super-Earth that is transiting and the outer eccentric long-period Jupiter. And this is a spectacular element of the synergy between techniques that is beginning now only to become available when the data are of sufficient quality. And I think I can stop here